we as a group have decided to build and train our own system to recognize and capture Ontario license plates from a source image. We believe it will be useful because it not only captures the plates, but also formats them consistently and outputs the files for further processing or inspection. Furthermore, we also believe our application is useful because it is specific to Ontario. Our project is based on Chapter 5 of Mastering OpenCV with Practical Computer Vision Projects. Although our idea is similar in design, we have built it around our own interpretation of how computers can see and classify license plates. Our unique contributions will be explained further in detail in the next section. As stated before, we have built our application mostly from scratch, using our own algorithms for license plate recognition. This will be explained in further detail in our quick code walkthrough in a future section. We have also trained our model with a unique dataset. It consists of example Ontario license plates, old and new, selected from the internet, as well as some original contributions. In our demo, we'll be quickly going over the 5 steps of how we get to our image classification. As you can see, the first step that happens is finding the edges. The edge maps are defined here. As an example, on an image of plate 1, this image is turned into black and white, and then the resulting output file of the edges is this. These thin white lines are what we'll be using our first computer vision implementation on. It's important to note that our getEdgeMap function also calls OpenCV's function morphologyEX. The reason we call morphologyEX is so that we can perform what's called a morph close. Our next step is step 2, contours, finding the bounding boxes. We can see finding the contours here, using possible viable contours. That function is located here in check region. Possible viable contours uses OpenCV's find contours method, as well as an additional check by us. This is a check done in-house to see if the rectangle is within our specifications of expected values, and the resulting contour images are here. As you can see, there are quite a few false positives, but hopefully our SVM trained machine will be able to identify them and classify them as not license plates. The third step in our algorithm is to find the masks. The main function we'll be running though is a flood fill. After the flood fill is complete, we will have our mask images, and using those mask images, we will move on to the next step, finding the segments. Segmentation can be seen here. This is where we transform our images into pixel matrices of 1D arrays. We will be using these 1D arrays to feed into SVM so that it can predict whether it is a license plate or not.
Once we collect all the candidate image segments, we classify them using an OpenCV's built-in support vector machine, or SVM for short. SVM is a classification algorithm that works by way of a supervised model. We prepare the model by providing 2 parallel datasets: our training data and our labels. First, let's start off with the training data. Our samples consist of plates and non-plates. The non-plates can be any car component, which could be fenders, bumpers, lights, hoods, trunks, you name it. Each image sample is 750 by 375 pixels, the same size as our candidate images after post-processing in the earlier stage. Before we feed this data into SVM, we need to do some processing. We need to convert each 2D image into a 1D feature matrix. For simplicity, we assume that each pixel in the image is a feature. So if every pixel is a feature, That would mean we have 750 times 375 pixels, which is 281 250 features. Thus, after collapsing our 2D matrices, we end up with 1D matrices with a length of 281 250. With all the resultant 1D feature datasets, we construct a 2D feature matrix where each row is a 1D feature matrix. Now, the training data is ready. Now let's talk about the labels data. The labels dataset explicitly categorizes the corresponding entry in the training dataset. For instance, we can couple this first one with the first sample image, this plate here, to learn that this pattern of features represents a registration plate. SVM would know it's a plate because the labels entry has a 1. If it contained a -1, then the corresponding entry in the training dataset would not be a plate. Now we can pass our data off to SVM. When we do that, it will build a model using the patterns it notices with the 2D feature set. We can conceptualize the model using a Cartesian coordinate system like so. Each plotted point represents one of the rows in our feature matrix. This hyperplane separates the grid into 2 separate regions, one for each category. Once the model is created, it can start making informed guesses based on the feature pattern it sees in the model. So, you can see this is a plate, and using the patterns that it learned from the data we provided, it can deduce that it is indeed a plate. In contrast, this is not a plate, obviously, to us, and SVM can determine that itself, again, from the data we provided.
My name is Daniel Sagan, and now I'm going to be talking about optical character recognition and its implementation into our project. Now first, I'm going to talk about the background of optical character recognition. Also known as OCR, it's used to identify characters or text in an image. It's been implemented as far back as the late 1800s, when it was used to allow blind folks to read without the use of Morse code. Now in the context of our project, we now have the use to extract license plates from an image, so we can identify the license plates, get their bounding box, and save the license plates specifically as an image. Now that we have these images, we need to be able to read what's on the license plates. Now, OCR has several real-life applications. One is with toll roads. For example, if you're driving along the 407 and you don't have a transponder, then the province needs to know who to send the bill to, so they'll have to recognize your license plate from an image. Another example is with red light cameras. They'll need to know your license plate in order to send you a ticket. And finally, with parking violations. Some parking lots, instead of using traditional tickets, instead detect the license plate and send you a bill that way. Now for the OCR implementation in this project, I use Tesseract. Tesseract is an open source OCR engine that's sponsored by Google and was originally developed by HP in the 1980s. It is now considered the industry standard for open source OCR. Now there are 5 steps taken in the implementation of OCR. The first step was to collect data. This was done by going around to different cars and taking pictures of their license plates. This was done from different angles and in different lighting. The second step was to label the data. This was a tedious process involving meticulous labeling of each character for each image. The third step was to train the model using the collected and labeled data. The fourth step was to test the model, and finally, to evaluate the performance of the model. Now for a demo of the OCR implemented for this project. Now from our project folder, we're going to run the command python ocr.py plate1.jpg. Python, which is the command to run a Python script, ocr.py, which is our Python file containing the script, and plate1.jpg, which is our sample image. Now when we hit enter, it's going to run. First, it has to recognize the plate, and then once it recognizes the plate, it will extract the text. Now we can see the extracted text here is sales rep. If we go into our test images, you can see that for plate 1, it is in fact sales rep. Now we want to go check out our output next. When we go into the output folder, we're going to look at the OCR output, and we're going to see plate1.txt. And that's just further confirmation that it is in fact sales rep. Now when you go into the plate folder, you'll see that there's two images. The first image is actually an error from our plate detection algorithm, but that's actually okay in this instance, as it's not a bad thing to have false positives. When you look at our other image, you'll see that it is in fact the plate that we're looking for. Now throughout this project, I learned several lessons about optical character recognition. The first lesson is that OCR is hard. I thought it was going to be a relatively trivial portion of this project, but in fact, it ended up taking me much longer than I thought it was, and it was quite difficult to implement. However, OCR has come a long way since early implementations. There's no doubt that in the 19th and 20th centuries, methods were nowhere near what they are today. However, OCR still has a long way to go. While OCR is very helpful for automation, there is no doubt that humans are much better at recognizing text than computers are. And finally, I learned that the best OCR engines are proprietary. For example, when you use your iPhone to detect text, that is Apple's proprietary algorithm. While Tesseract may be the best open source OCR engine, there are still many engines out there that do perform better than open source versions.
I will now be taking you on a quick demo of how our system works. We were using Replit to collaborate, and Replit has an online compiler. All we need to do is hit run, and when we hit run, we can see that our output folder is cleaned so that we can see our new output. Then in order, it trains the SVM, finds the edges, finds the contours, the viable masks, and then cross-references the plates we isolated with our SVM. Once our program is done, it tells us to check the output folder to see the results. Just so that we can see what we're working with, since I hit run with no arguments, it'll run on the default test file, which is plate 1. Once again, this is what plate 1 looks like. And in order, it finds the edges, then finds the contours, then finally converts those into masks, and then converts the masks into segments, which are fed into our SVM, and the SVM determines whether they are a plate or not. And there we go, it has successfully detected that this mask was a plate, and this one as well. However, it has misidentified this logo as a license plate. And these false positives will be explained further by Nicholas.
Now let's discuss how fine-tuned our algorithm is. Here's our confusion matrix. In the context of registration plate detection, a true positive means the application correctly predicted a plate. A false negative means the app failed to detect the plate. A false positive means the app took a car component for a plate. And finally, a true negative means the app correctly predicted a non-plate. Let's take a look at successful use cases first. So in this first one, we have a picture of the rear of a Lexus, and as you can see, it got the plate. Now you may notice the plate looks a little strange, and that's because we resized the image to a constant size of 750 by 375 pixels. as mentioned in the previous analysis of SVM. Okay, moving on. Here's an image of the rear of a Toyota Highlander. So as you can see, we do in fact get the plates. And this plate looks normal just because the plate in the original image was larger because I took it at a closer distance than this one, which was a lot smaller. Now you'll notice that we also got another image of the brand icon of Toyota. Our algorithm mistakenly thought that this also was a plate. We assume it's because of the large amount of highly saturated white pixels. Now let's take a look at failed cases. We notice that cars with a mostly solid color tend to fool our algorithm often. So as you can see, we just can't detect these plates here. So therefore, we regard them as false negatives. We've also noticed that distortion caused by external weather events, like a snowy day, prohibit our algorithm's ability to detect plates. So as you can see, same results, no plates. So it is a false negative. So in short, our algorithm only works best in ideal situations.
This experience was a great chance to get ourselves some hands-on experience working on computer vision. For us, it was a challenging experience but fun to problem solve. If time allows it, we would like to continue working on our project to meet its original goal of identifying license plate stickers.